There are several different strategies to solve an exponential equation when that x is stuck up there in the power. We're going to use two different strategies for this example. The first one is that a log base a and an exponential base a are inverse functions. They undo one another and give me x back. The second strategy I need is the definition of the logarithm. This says that log base a of x equals y means that a to the y is equal to x. I'm going to apply this first inverse function property on our example here. So I've got 3 to the x plus 2 on the left-hand side. To undo that, I need to apply a log base 3. So I'm going to apply a log base 3 to the left-hand side. Whatever I do to the left, I need to do to the right-hand side as well. This works out really nicely because the log base 3 undoes my exponential base 3, and I can bring that x plus 2 down on the main line. So x plus 2 is equal to log base 3 of 81. Now I'm going to use the definition of the logarithm to get at what this means. So if I rewrite this, this would say that, let's see, log base 3 of 81. So this would say 3 to what power equals 81. Well, I know that 9 squared is 81, so if I did 3 to the 4th, this would equal 81. If this doesn't work for you, you can also use a change of logarithm. So you can also write this as log 81 divided by log 3 and put this right into your calculator, and you are going to end up with a 4. So this is a 4. So what do we have? We've got x plus 2 is equal to 4. If I subtract a 2 from both sides, x is equal to 2, and this is our answer. Exponentials are nice because they have no domain restrictions. We know that we can go ahead and keep a solution once we've got it. Let's take a look at another one. This next one is really similar to the last one, but there's a couple of different changes. I do have that x in the power, so I need to use a logarithm to undo that. And I also have this 2 here out in front. The very first thing that I want to do is to divide everybody by 2. So if I divide everybody by 2 here, I end up with the e to the 3x plus 4. I've got that exponential isolated, and I have 4 on the other side. Now, e is associated with the natural logarithm. So if I want to put the inverse property up here, it would be the natural log, which is base e, of e to the x. These are inverse functions, and it gives me whatever is in the power back. So I want to apply a natural logarithm to both sides of this equation. So I'm going to apply a natural logarithm to the left-hand side, and I think I can just barely squish it in there, a natural logarithm to the 4. Okay, so what does this give me? The natural log and my exponential base e, they cancel each other out, and I'm left with a 3x plus 4. On the other side, I have my natural log of 4. Now there's nothing else that I can simplify with that natural log of 4, so I can keep going and isolate my x. I need to subtract a 4 from both sides. So I end up with 3x is equal to the natural log of 4 minus a 4. You cannot combine those 4s. The first one is trapped inside the logarithm, so we're going to leave it just like this. And then finally, I need to divide everybody by a 3, getting that x isolated. So we end up with our solution. X is equal to the natural log of 4 minus 4, all divided by 3. Now this is my exact answer. If I wanted to get an approximate answer, I could either put this into my calculator. I've got my TI-84. Any calculator would work that is a scientific one. Or I love Desmos, so you can also put this into desmos@desmos.com. Let me put it into my TI-84. When I put it in my TI-84, I need parentheses around the numerator so everything gets divided by 3. So I'm going to do parentheses, and then I grab the logarithm, the natural log, which is next to the 4. So natural log of 4, I need to close the parenthesis for the natural log, and then I've got minus 4. So minus 4, close parenthesis, and then divided by 3. So our approximate answer would be this negative 0.8712 if you rounded it to 4 decimal places. In this one, I've got two different bases. One is a base 2 and one is a base 3, and both of them have an x up there in the power. So I want to go ahead and isolate these, one exponential on each side. So I'm going to move that 3 to the x over by adding it, so plus 3 to the x. This gives me 2, 5x minus 1 is equal to 3 to the x. I need another property of exponents here. The property that I need says, we're going to use a natural log because it's really easy, it says the natural log of a to any power. I can bring that power out in front. So this equals n natural log of a. And again, you can put any log in here. The property works the same. So I really need a logarithm out in front of both of these. I'm going to apply a natural log on both sides of my equation, and I think I've got enough room just to go ahead and do it right in line here. So natural log right in line there. Now that I've done that, I can take this power on both sides. On the left, it's the 5x minus 1 and bring that out front, and I can bring the x here out in front. Now I need to put the 5x minus 1 in parentheses because it is a quantity held together. So 5x minus 1, natural log of 2 is equal to, I'm going to bring the x out in front, so x natural log of 3. Next, let's multiply that natural log 2 into these parentheses. My goal is to get x's on one side, anything that's not an x term on the other. So as I continue to simplify here, I get 5x natural log 2. And now the negative 1 times natural log 2 is minus natural log 2. Nothing on the other side has changed, so x natural log of 3. Okay, where are my x terms? So I've got an x term here. Natural log 2 is not an x term, and I have an x term there. Let's subtract the 5x ln 2 to the other side. So I get my x's on one side, and I'm going to leave that non-x term, natural log of 2, on the other side. Okay, so keeping everything straight here, I end up with minus natural log 2 is equal to x natural log 3 minus 5x natural log 2. What I'm going to need to do next here is to factor out that x. I don't want a couple of x's, I want just a single x. So I've got an x here and an x here. I'm going to divide both of these by that x, and then I'm going to move the x out in front. You can just think of this as factoring that x out in front. No changes to the left-hand side, so I get equals natural log, or negative. So I get negative natural log 2 equals, let's put that x out in front. So x, and then what am I left in my parentheses? I am left with the natural log of 3, so natural log 3, minus I am left with the 5 and the natural log 2, the 5 and the natural log of 2. X is almost isolated. I just need to divide both sides by the natural log 3 minus 5 natural log 2. Here, this is going to be natural log 3 minus 5 natural log 2. Okay, so what does my solution look like then? We have x is equal to everything up here. So that's going to be natural log of 2, all divided by parenthesis, natural log of 3 minus 5 natural log of 2. Let's go ahead and put that one into our calculator so we can also get an approximate solution. Okay, so here's my calculator. I just have the single quantity in my numerator, so I can go minus natural log of 2, close those parentheses, divided by, I need parentheses around the denominator. So just exactly like I've got it there. So parenthesis, natural log of 3, that opened with a parenthesis. So I'm going to close that one. And then I had minus 5, natural log of 2, natural log next to the 4 there of 2. Close the parenthesis for the natural log, close the parenthesis for the denominator, and I get my approximate answer of 0.2928. Here comes another example. In this next example, again, x is trapped up there in the power, but we have a single logarithm. If you are feeling good about these, go ahead and pause the video, work through it, see what you get and check back. Otherwise, you can follow along with me. Since I've got a single exponential here that's base 10, I'm going to go ahead and use the logarithm base 10. Logarithm base 10 is my common logarithm, just log. So if I do log of 10 to anything, I end up with an inverse function, and I get just an x back. So I'm going to go ahead and apply an log, that common logarithm, to both sides of this equation. So log of 10 to the 3 plus x equals log of 7. Now my functions on the left-hand side cancel each other out, and I get 3 plus x back, and I end up with log 7 on the other side. This turns out not to be a nice number at all, so I can go ahead and keep solving. I want to subtract a 3 from both sides, and I get x is equal to log of 7. I cannot combine that 3 with the 7 because it's trapped inside the logarithm, so I end up with this expression. I want to show you another technique for this one. We do have two different bases here, but we can use a technique getting like bases. You'll notice that 3 squared is equal to 9, so I can rewrite the second exponential expression using a base 3 instead. Here's what it looks like. So I'm going to go ahead and just leave the 3 to the x, but I can write 9 as 3 squared, and then I get an x plus 5. Well, whenever I've got a power of a power, like I do on the right-hand side, I can multiply these two powers together. So I get still 3 to the x on one side is equal to 3, multiply that 2 through, 2x plus 10. Now, because I have like bases, I could go ahead and apply a log base 3 on both sides to undo those, but I can also say if they have the same base, they also have to have equal powers. So now I can just go ahead and bring down both of these powers and say, you know what, they need to be equal as well. So x is equal to 2x plus 10. Let's go ahead and solve this. So I'm going to subtract that 2x from both sides. That would be a 1x, so 1x minus 2x is negative 1x is equal to 10. Divide both sides by a negative 1, or just swap your signs around, and x is equal to negative 10, a really nice quick way to go. I've got one more for you. This particular example is here because it comes up a lot when you're doing compound interest problems. Notice that I've got that t, which represents time, trapped up there in an exponent. So I know I'm going to need to use logarithms here, but I want to follow my order of operations. Let's go ahead and do this, the quantity in parentheses first. Now I already did that. I went ahead and put that into my calculator. Let's see, I'm going to leave the 2000 here, and 1 plus 0.05 divided by 4 is 1.0125. Okay, so I've got that simplified. The next thing that I want to do, again, I'm isolating where my exponent is, where my t is. So let's go ahead and divide both sides by 2000. So I'm going to divide both sides by 2000. I want to get that exponential all by itself. 10,000 divided by 2,000 is 5, so I get 5 is equal to 1.0125, all to the 4t. Okay, so now things are looking really good. I've got my exponential all by itself and a number on the other side, so I'm ready to apply a logarithm. I'm just going to use a natural logarithm here because it is easy to put into my calculator. So I'm going to apply the natural log on both sides. Okay, so what do I get? Just the natural log of 5 on that side. On the other side, I can bring that 4t out in front. So I get equals 4t natural log of 1.0125. Now my goal was to solve for t. There it is. Let's divide by everything else. So I want to divide off the 4, and I want to divide off the natural log of 1.0125. And I'm going to do this on the other side as well. So 4 natural log 1.0125. I'm going to put this into my calculator. When I do, I need parenthesis around that denominator. So t is equal to what we've got over here on the left-hand side. So let's go ahead and put this quantity into our calculator. I'm going to go ahead and let me clear what I had there. We're going to start with the natural log of 5 up in that numerator, and then divided by parenthesis 4, natural log of 1.0125. Close our 2 parentheses, and we end up with about 32.39 years. You guys are doing so great. Take a look at this next video on solving logarithmic equations. Thanks for watching.